So on my next question right here, I could definitely write an explicit formula because this has a common difference of -7. But it says to write a recursive rule. So for recursive, I need to actually state what my beginning term is. My beginning term is 25. And then I write my pattern based on the term right before. So the term right before 18 is 25, and to get from 25 to 18, I'm actually subtracting 7. So this would be my recursive equation for that. I know I said not to worry too much about the summations right here. So this would be a series. It's different than a sequence. A sequence is just numbers in a list. A series, we're actually going to be adding those numbers together, but I think that this is useful to actually introduce that idea. So my subscript on the bottom is telling me where I'm starting. I starts at 1, and I'm adding together all the values of when I plug in 1 to when I plug in 5 up here. So I'm going to plug in 1 first. Now I'm going to plug in 2. I'm going to plug in 3. And I will stop when I have plugged in 5. So I know I'll stop when I have plugged in 5. So now this is just a matter of doing some algebra. I think that ends up being 40 when I add all of those together. Okay, I love this last one. I love looking at patterns that we have here. So pause this video, try this on your own before we actually get started on it. Thinking about this as a 1 by 2. Let's see, this is a 2 by 4 now. This is figure 3, and it's a 3 by 6. So in figure 43, I'm going to have 43 rows right here. And then it looks like it's going to be double that. So 43 times 2 columns. So our whole pattern would be n times 2n would be like our sequence pattern, but it's just asking for what 43 would be. If I multiply that together, I think it's 3,698 squares. Okay, so far we've actually just been looking at either constant terms or ones that have a first difference or a second difference. So our first difference would be linear. And so here's an equation that we could actually use for that. You could say, hey, our starting first value plus our common difference, so D is our common difference, times our n minus 1. Another way of actually doing it is if I start with my 0th term, so a lot of times it just starts on the first term, but if we go backwards and we start with our 0th term, then we only have to add our common difference n many times instead of n minus 1. You don't have to worry too much about this partial sums until our next section, but this is like an explicit rule for that. Okay, this last little problem I wanted to look at, it says find the 7th, 8th, 14th term in our sequence. We're adding 4 each time and then write an explicit rule for the sequence. So we can actually see what we start with is this 2, that's our a sub 1. So our pattern would be we start with 2, we're adding 4 each time, but I want to add 4 n minus 1 many times. So by the time I get to the 7th term, I'll only have added 4 6 times if I start at 2. And another way that I could have done that is I actually could have gone backwards and found my a sub 0, which would have been -2, and now I can just add 4 n many times, and you can see that these are actually equivalent to each other. Maybe some of you have heard of the Fibonacci sequence. Fibonacci sequence is actually found in nature a lot. So like if you cut open a pineapple or you look at a pine cone, the ratio that is between the inside seeds to the outside seeds, or the inside part of the pineapple to the outside part of the pineapple, or even Mona Lisa, the ratio between those is actually what we call the golden ratio. And that has to do with our Fibonacci sequence. So right here, Fibonacci sequence is I start at 0. That's my 0th term, and then my first term is 1. And then what I do is for my next part, or my next term that I have, I'm adding my 2 previous terms together. So to find this third term, a sub 3, I'm going to add together a sub 2 plus a sub 1. I'm adding together my first 2 terms. So 0 plus 1 is just going to be 1. So now to find my fourth term, I'm adding together my previous 2 terms. 1 plus 1 is 2. 2 plus 1 is 3. 3 plus 2 is 5. 5 plus 3 is 8. And I think we've actually already gotten, we're almost there. 8 plus 5 is 13. So any of these ratios between these is actually going to give us this lovely, lovely number. That's a phi right there. It is Greek. It goes on forever, just like pi, just like e, but it has to do with the ratio between these numbers, and that's found in nature. I thought that was kind of cool. On these next 2 problems, I'm actually just going to write out the work because I feel like we already got this experience in the check your understanding up above. Okay, so first one, not too bad, just plugging in values. We start at n equals 0 and then go out towards infinity. So we could say dot, 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 but we're just looking at our 5 first terms. This next one, I actually wrote out the sequence right here, and then we can see that the first difference is that we're adding 4 each time. So I'm going to have a 4 as my slope, or as my common ratio. And my a sub 1, what I started with was 3. So I'm going to start with 3, and then I'm going to add 4. By the time that I've gotten to this 11, I've only added 4 twice. So that's my third term. I've added 4 twice, so I need to add 4 n minus 1 many times, 1 less than what the number in the term is. Another way that I could have done this is I actually could have found my 0th term, so a sub 0, by going backwards and subtracting 4, and that would be negative 1. So negative 1 will be where I start, and then I'll just add 4 n many times to get to that term in the sequence. So if I look at starting here, 1, 2, 3 times, I'm adding 4 to get to 11, so that's my third term in the sequence. You don't have to worry too much about this little epsilon. That is used in some higher math level classes like abstract algebra and complex analysis, so you don't have to worry about it too much. It's just saying once we get arbitrarily close to our limit, so a sequence can bounce all around, but if it's getting arbitrarily close to a number, L, then we can say that's what it approaches. And we can say that if our function converges to L, then our limit, or our sequence, also converges to that L. Our algebraic limit laws are also the same as our series, or like when we were doing derivatives. So if I'm taking the limit of 2 different sequences and adding them together, I can take the limit of each of those, find that, and then add them together. Works for multiplying, works for dividing, works for having a constant out in front. So if this was just like a 3 and then I had some sequence, I can pull the 3 out in front and then take my limit of that sequence. And here's some examples on that. So if I look at, does this sequence right here actually converge? Well, it does, because our limit is approaching 1. So if I look at my limit of that sequence, I can use L'Hopital's because it's infinity over infinity. So derivative of n is 1. Derivative of n is 1. Derivative of n plus 2 is also 1. So that's how I know that my limit is actually going to be 1. Does this sequence actually converge? Well, what is getting bigger faster, 2 to the n or n squared? And exponential always beats any sort of polynomial. Exponential gets big really, really, really fast as n approaches infinity. So this is gonna, my top part, my numerator is getting bigger than my denominator, so it's gonna be approaching infinity. It does not exist. And last, we saw this in the Check Your Understanding. It is called an alternating series, or an alternating sequence in this case. And it's just gonna go back and forth between -1 and 1. So it's not actually approaching anything, it's just alternating back and forth. That also does not exist, but it doesn't exist in a special way. We can't say it's approaching infinity or negative infinity or 1 or -1 because it's anything in between. I thought these would be valuable to actually look at. So if we look at our limit of each of these, we can actually, as n is approaching infinity, we can see if the sequence actually does converge. So as n approaches infinity, I'm going to have 3 over a huge number. This is actually going to go to 0. So I will end up getting cosine of 0, which is 1. So this does converge. It converges to 1. Okay, on this one, again, our exponential is getting huge. So on my numerator, big numerator, not as big denominator. So this is actually going to approach infinity. Okay, if I take a look at this one, I already know it's going back and forth between, well, hold on, we're going to take a look at this. So this part is in between -1 and 1. But my n plus 1 here on my denominator, I can actually break this into 2 different things. So I can look at this limit times my limit as n is approaching infinity of 1 over n plus 1. So this is between -1 and 1. It just alternates back and forth. But my limit of this is actually going to be approaching 0 because I have a really, really big denominator. As n gets larger, I'll have 1 over a huge number. So that approaches 0. My 0 kind of takes over. 0 times anything is just going to be 0. So this does converge. It converges to 0. Okay, last but not least, I'm going to take my limit as n is approaching infinity of this whole thing. And if I kind of plug in my infinity, I'm going to have a huge number at top, huge number at bottom. It's unclear which one's getting bigger at a faster rate. Since it's infinity over infinity, I can actually use L'Hopital's. And I can take my derivative of the top over my derivative of the bottom. Derivative of the top would just be 1 plus, and then I think that's going to be 3 times 2n ln of 2, and derivative of the bottom, my 1 just goes away, and so I would have 2n times ln of 2. And I think I'll just need to take my derivative one more time because it's still in indeterminate form, infinity over infinity. So I'm going to take my derivative one more time, and I'll actually get a 3 is constant times, I'm just taking my derivative of n, or 2 to the n, because my ln of 2 right here is a constant. So my ln of 2 is a constant, and now I'm just taking my derivative of 2 to the n, which is 2 to the n ln of 2. And then here on my denominator, my ln of 2 is my constant. Derivative of 2 to the n is 2 to the n times ln of 2. And we can actually see a lot of stuff ends up canceling out. My limit is just going to be 3, so this does converge, and it converges to 3. A few other things to talk about. So if I have a middle of my sandwich, I have a top of my sandwich and a bottom of my sandwich, that middle is always going to be in the middle. So it's kind of like this squeeze theorem for sequences. If I have a sequence on top, and I have a sequence on bottom, and I have a sequence that's always in the middle between them, then they're all going to converge to the same thing. Or my top and my bottom converge to one thing, that middle is also going to converge to the same thing. So for example, right here, if I throw this in with 2n minus 1 over 2, if I throw this in between these two sequences. So this is always going to be in between, because my sign just alternates between -1 and 1. So 2n plus sine of n over n. Well, this thing converges to 2. This thing also converges to 2. So my middle one also has to converge to 2. It's like a sandwich. Just a few more vocabulary words. So we can have bounded above sequences that they are always below a certain value. We can have bounded below. And then if a sequence is bounded above and below, we just call it bounded. If a sequence goes off towards infinity, it is not bounded. So it's an unbounded sequence. Or that alternating sequence that we talked about where it went -1, 1, -1 and 1. I guess that is bounded above by 1 and below by -1, but it's also not strictly increasing or decreasing. It's just going back and forth. And when something is increasing versus decreasing, actually I wanted to talk about that, that is called a monotone. So if somebody talks really monotone, they talk kind of flat. And a sequence that is monotone, it is either always increasing or always decreasing. There's a really cool theorem that says that if we have a monotone bounded sequence, it converges, because it's bounded between two things and it's always increasing, always decreasing. Not going to be that alternating series or alternating sequence that we have, that it's always going to converge. So if a sequence converges, then it's forced to be bounded, but it's not necessarily true the other way, because this is bounded between -1 and 1, but it is not convergent. It's only when you get the bounded and the monotone, so it's either strictly increasing or strictly decreasing, that you can actually show convergence. If we have a little r value, as long as that r to the n value, so if it is larger than 1, then it's going to diverge, because it's just going to keep on getting bigger as it's getting raised to the nth power. So that would be something like this. It's just going to go off towards infinity, kind of like an exponential. And if we have it is bounded and it is in between -1 and 1, which is another way of saying that the absolute value is less than 1, then we're going to have something like an exponential value that is decreasing over time, and that's why it'll converge. Okay, very last example that I wanted to talk about, this monotone convergence theorem. So it has to be monotone and bounded, and then we can say that it actually converges. So this little explanation point is factorial. It means we're multiplying all the numbers below that n value. So if n was 10, it would be 1 times 2 times 3 times 4 times 5 times 6 times 7 times 8 times 9 times 10, all the numbers that are below 10 that I'm multiplying together. So I just want to write out the first few terms of the sequence. If I start at 1, I'll just have 1 factorial, which will be 1. N equals 2 is going to be 5 over 2 factorial is 2 times 1. I have 5 over 3 factorial is 3 times 2 times 1, so 6. 4 factorial, I'm multiplying 1 times 2 times 3 times 4, and I think that's going to be 24. Yep. And so we can already see that this is actually approaching some value. So it's like they're single points, they're not actually connected. So that's continuous, but sequences are not connected, they're discrete. So it's kind of looking more like this. And what is it approaching? It looks like it's actually approaching 0. So I have its monotone, I have that it is bounded below by 0 because my denominator is getting larger and larger. So I can say that this actually approaches 0. It is convergent, that is its limit. Okay, y'all, I hope you have a beautiful day. Bye.